Hello, everyone, and welcome to the Unlocking Business Value with Graph Databases webinar. So before we get started with the event today, let's just take a quick look at our agenda. So we'll start off with a brief introduction at Thorogood for those that aren't familiar with us before getting right into an introduction of graph and graph databases. We'll start with some high-level concepts and ideas that come with graphical structures before diving into some of the graph algorithms that can be applied easily on top of graph data to really unlock some of that business value that's possible with graph data and the study of networks. Then to close us out, Jake will introduce a business case where we'll dive further into some of the concepts and technologies that we discussed during the earlier part of the session. So to briefly introduce ourselves, my name is Brendan and I am a data and AI consultant at Thorogood. I'm joined by my colleague Jake, who is also a data and AI consultant. We're presenting today out of the US. I'm based out of Thorogood's Boston office and Jake out of our Philadelphia office. And we both have experience in delivering data and AI solutions for our clients. And we're really excited to dive into Graph today with you all and how it can really help to unlock some value for you and your organization. And for those of you who do not know Thorogood, we are a global independent consultancy firm specializing in data and AI. We combine our business focus with best-in-class technological solutions to solve complex business problems. And we blend our business understanding with strong technical aptitude with a deep understanding of analytical tools. We're a global company with offices in London, Boston, Philadelphia, Bangalore, Singapore, and Sao Paulo in Brazil. And we offer a full range of services across the entire data and analytics spectrum, including strategy and roadmaps, requirements, design, implementation, and training and support. Many of our clients are in 4 different types of industries: consumer goods and manufacturing, pharma and healthcare, banking, and insurance. And of course, we're not limited to these 4 verticals, but these industries typically lend themselves to being very data rich and are constantly seeking out creative ways to use data and AI in their respective industries. And as I mentioned, we are an independent consultancy, so we maintain close partnerships with many of the key vendors in the data and AI space. And these are just to show some of the major technologies that we work with. And our independence really means that we can identify the best possible solutions for our customers based upon their needs. So that's a brief intro to Thorogood. So I'll kick us off here with our topic of interest today, graph. So before we get into what graph databases are and what some of their use cases may be, let's first orient ourselves with something that may be a bit more familiar, a table. You could think of something like an Excel sheet as the most common tabular structure that individuals may use on a day-to-day basis. And fundamentally, a table is a data structure that is made up of rows and columns. Rows represent the number of records in a table. So in our example here, we can see we have orders and some information on them. And on columns, we have some different attributes and KPIs for that given record. So we could have the total number of goods bought and their costs. We could even have other descriptive information as well, like what was included in the purchase or where it was purchased or something like that, right? But it's more than just one table, right? We can also just relate these tables to others, as the name suggests, within a relational database via keys that have been defined through a join to derive even more meaningful information and inform certain analyses that would just not be possible by looking at information from one table. And by bringing this tabular data together by writing a query in something like SQL or Python, we can really begin to slice, filter, and aggregate data to derive meaningful insights to answer some key business questions. Almost everyone will probably be familiar with tabular data and subsequently the reporting that can be surfaced through relational databases, even if we're just familiar with some of the table structures that actually make up a relational database. However, not everything can really be represented within a traditional table. So let's take a quick look at what's probably a familiar example for many of you, and that's organizational structure. We can imagine what an org chart looks like within our head, but it's a bit complicated and hard to really derive much meaning very quickly with it represented as a table. Because I've already colored it here, I can see that there are 2 pillars within this organization, sales and finance, that seemingly roll all the way up to the top with James as the CEO. Now I could begin to map it out and try to self-join the table with itself to map out the full hierarchy, but it gets very complicated very quickly, particularly when I want to understand the hierarchical nature of this organization. So by self-joining this table onto itself a few times, we can see that Michael rolls up directly to a finance director, whereas Elizabeth has an intermediary sales manager that she reports to. It's a ragged or an uneven hierarchy when we go up the organization, which makes the potential join conditions even more complicated. So we'd really struggle to bring this into a traditional reporting solution, given that the relationships are flexible and ever-changing, as people are constantly changing who their managers are and who they're reporting to. But another challenge within this is that level 1 for Michael takes on a different meaning than level 1 for Elizabeth. So the levels lose their meaning and they can't really be compared to one another very easily because level 1 will take on a different meaning potentially for every different employee. And ragged hierarchies like this one are really a common representation of data that tabular data structures really struggle to represent neatly. Another example would be a circular relationship, and that's also very challenging to represent cleanly within a tabular database. That's not to say that this tabular data isn't useful. It's able to tell us the different roles in which an employee may have and who their direct manager is. But when we want to focus on understanding the underlying relationships within our data, we would consider storing this type of data within a graph database. So by breaking this down to instead an analysis focusing on the hierarchical relationships between employees and their managers, this becomes a much easier problem to visualize and interpret. It's much easier to see who reports to who and the nature of the different relationships that we're trying to understand. Our data naturally lends itself to being represented within a graph database as opposed to a relational one, as is the case with other business problems that rely on analyzing underlying relationships within data. So this is really where graphical representations of data thrive, when we want to understand the network and its underlying relationships as opposed to just the elements of data itself. So maybe before we even get further here, let's pause and delineate what we mean when we say graph. Graphs and graph databases in this context and what we'll be talking about in this session refer to the application of the mathematical meaning of graphs, which is different from what a graph may mean in the visual sense. Graphical structures are used to model relationships between different entities. And those graphical structures consist of data in the form of nodes, edges, and properties. Those three structures allow us to derive and analyze meaningful relationships in data that can be represented within a network. So first we have our nodes, which are the vertices of our data, and edges are the links that bring them together. And nodes and edges can assume a variety of properties that are descriptive, like a given location, or quantitative, like units sold, or something as well. I think something that's really powerful when representing our data as a graph is that relationships can be formed between nodes of different categories. So in this organizational hierarchy example from before, in one graph, I'm able to represent employees in looking at Michael and Alexander and who they report to, with an edge indicating that they report to Noah. Additionally, in the same graph, I can also clearly illustrate a different type of node and edge to illustrate that Noah's home office is in Philadelphia. So we'll dive into the ways in which we can define multiple types of nodes and edges within the same graph within a use case later as well. But at the end of the day, these nodes, edges, and properties can be stored within a database that's built for this purpose. So much like how we have relational databases to hold our tables, we have graphical databases that can hold our graphs. So this isn't meant to be an exhaustive comparison of graphs and relational databases, but let's briefly talk through some of their similarities and their differences. As we've discussed, graph databases hold the interconnected web of nodes, edges, and their properties. The data structure of a graph is just different than that of a table, and we have databases and technologies built to be able to optimize the storage of this data. And within a graph database, this optimization partially comes from the fact that the relationships between our different nodes are physically stored within the database. We don't need to join tables together on keys to bring our data together like we would in a relational database. And physically storing these relationships really allows for querying and analysis to happen directly on our network of data. And because we store these edges or relationships within our database, we don't need to do any additional computation to see them. And that's not to say that we can't get to the same result via multiple joins or complex queries, but as we saw with the organizational hierarchy example, it can get really complicated really quickly. And that could even be compounded by the fact that it could be very computationally intensive as well, particularly when we want to join dozens of tables together across tens or even hundreds of millions of records. And like a relational database, we can also write queries using languages such as GSQL or Cypher to query our graph database. The syntax, of course, will be different than SQL, but it's still an option for us to be able to conduct more exploratory analyses. And finally, where we will be going next with our session today is that graph databases lend themselves extremely well to the implementation of graph algorithms. The graph algorithms are ways for us to really dig deeper and understand our graph data. So before we get into that, I'm going to turn it over to Jake briefly to just see these foundational concepts of nodes, edges, and properties in a quick demo.
Thank you, Brendan. Let's jump right in. So in this example, we are a car and truck manufacturer, and we want to have a better understanding of our supply chain. And in a graph, we care about a few key entities or nodes. We have components that are used and combined to make other components. So some examples will be raw materials like rubber or steel that get combined to make more complicated items like tires. We also have the different manufacturing sites that produce these components, and then finally deliver it downstream to other sites. I'll jump now into Neo4j, which is a graph database technology, so we can start to work with and visualize this data. Now that we're in Neo4j, we can go ahead and open up a perspective. We're working in Neo4j's Bloom, which is their visualization technology, which will let us work with and visualize our data pretty intuitively. So first, let's take a look at these nodes that I was talking about. We can visualize our data quite easily. So we have our components on screen now. And we can see sort of what I was talking about before. We have some finished goods like car wheel sets and tires. We have some intermediate goods like modules. We have a wide variety of components here, and this will fit into our overall supply chain. We can also go ahead and draw on our manufacturing locations. So now we have in our view here, both the lighter blue being the components and this green color being our manufacturing sites. And even though these are all nodes, they're nodes of two different categories or labels. The real value of having our data in this graph form is being able to see how these nodes relate to each other. Even though we have some dimensional information right now, we really want to be able to understand the relationships between these different attributes. So with that, we can go ahead and draw relationships between nodes of the same category and nodes of different categories. In our case, it would be relationships between components, relationships between sites, and relationships between sites and components. So with that, I'll go ahead and draw my component-to-component relationship, and I'm also going to change the layout to make it a little bit easier to follow. So if we zoom in on our component map, we now have a sort of bill of materials of understanding how all of our input components are used and created to create our final output items. So we can see if we work from steel rods are used by belts, which are used by tires in conjunction with rubber in order to produce our final car wheel and truck wheel sets. So we can sort of understand how our different components are coming together very quickly. Similar to the hierarchy example that Brendan was showing before, it's not necessarily a one-to-one or a certain number of levels between. Some goods or components may require multiple input components, others may just require one or two. I want to call out the relationship itself here because it's slightly new to graph and specific to graph and isn't something you can find in a relational database. We can create new attribution on our relationship itself and have the relationship take on new meaning as opposed to just doing a join statement where we can't really define anything physically. So I'll call our attention to the arrow of this relationship. We know which way the direction of the relationship flows. So we know that steel rods are used by truck rims and not the other way around. This is different than, say, a social network, where in a social network example, if we have two people that are friends with each other, the direction itself wouldn't have a ton of meaning behind it. But in our case, it does. The other thing I want to call out for our relationship is that we can add on attribution to the relationship itself. And what do I mean by that? Well, on each of our use by relationships, we can also include attributes like the use amount. So now we know how many of each input item do we need to produce the next one. So in this case, our example before, we need 10 steel rods to produce one belt, 200 belts and 100 rubber units to produce one tire, 16 tires to produce a truck wheel set, and 4 tires to produce a car wheel set. So in this way, we can start to understand how we may weigh and aggregate these different attributes in order to do some calculations. We'll go ahead and do some of these calculations in a demo later on. I'll go ahead. I mentioned our component-to-component relationships. We also have our site-to-site relationships, and this will tell us the flow of items across our network. So we can see, just tracing down, site 8 delivers to site 14, which delivers downstream to site 4, and finally to site 3. And similar to our other relationships, we can go ahead and store information on our relationship itself. So if I go to my delivers relationship, I can go ahead and show potentially the distance between two different manufacturing sites, or I can show the quantity of goods delivered. So site 5 delivers 11 units to site 9, 2 units to site 4, and 6 units to site 15. We can store this and any other attributes, including multiple attributes, on the same relationship, but for now I'm just showing one. I'll go ahead and build out our final relationship so that we can see the entirety of our graph. So this will tell us which components are used by another component, which site delivers to another site, and which site produces each component. And even in our small example with a relatively few amount of nodes, it's still pretty complex. It's still hard to get all of this in one visualization and to really understand the flow of our data. So visualizing our data in this graph form may be a useful way to explore. For right now, and especially as we add in hundreds of sites, thousands of components, it will get really complex. But where we believe the true value add is the ability to apply graph-specific algorithms that utilize this unique structure of graph and make it easier to pull insights from it. We'll come back to this manufacturing data set later on and layer in some more real-world use cases. But for now, I'll pass it back on to Brendan to introduce us to some of these algorithms.
Thank you, Jake. So as mentioned, we'll focus this next section on diving to 3 groupings of graph algorithms: path, centrality, and community. We'll introduce at a high level what each of them are and how they can be applied for a few examples. So with our data established and stored within graph structures in a graph database, these sorts of algorithms can be run easily to really help uncover and analyze relationships and connections within our data set. First, we have a path algorithm, which will traverse through a graph, identifying optimal and efficient routes to get from node A to node B. Then have centrality algorithms, which are more so measures of popularity or influence within a graph and their respective impact on the graph as a whole. And lastly, community algorithms take into account nodes and their relationships with one another to identify communities and related nodes. So with just a brief summary of each algorithm, we'll get into a little more detail with some examples to help illustrate what each of them are and how they can be applied in real-world context. So path algorithms, again, at a high level, are ways for us to apply logic to find the shortest or most efficient path between two nodes within a graph. And it may be easiest to think about this with the example of trying to ship goods across the country from Boston to San Francisco. Let's say we want to find the shortest route by distance driven between the two cities. For this example, our nodes would represent our cities where we may be dropping off product, and our edges are the road that we're physically driving on. With the proper relationships and routes established within the graph, we can algorithmically determine the most efficient or shortest path route to ship our goods across the country. But as we alluded to, nodes and edges can assume different properties. So while initially we may be interested in evaluating the shortest path between two nodes by miles driven, we may also be interested in evaluating the shortest path by kilograms of carbon dioxide consumed if we have a sustainability goal in mind. Or if we're focused on the pure time it took to ship goods from Boston to San Francisco, we can see that within our graph that shipping goods via air is the quickest method, reducing our shipping time to hours as opposed to days. So that's kind of a high-level example, but there are definitely other implementations of path algorithms that you're probably familiar with as well. And one of the most common implementations would be using a GPS to get from one destination to another. Google Maps or Apple Maps or Waze have your start node and your end node and are looking to find the shortest path between the two of them. Those apps are taking into account shortest path by time if you're looking to avoid traffic, or shortest path by money if you're looking to avoid tolls. Another example would be the idea of network routing, or the most optimal way in which signals and messages can be shared between people located around the world. And finally, something slightly different for our last example. I've mentioned shortest path a few times. The shortest path algorithm is one of, if not the most common implementation of a path algorithm within a graph. But another common one would be a minimum spanning tree. So if we take the idea of a post office needing to deliver all mail to all residents within a small town or city, we want to make sure that we visit all nodes or houses as efficiently as possible. So the efficiency is, the most efficient route that the delivery person takes in order to visit all nodes within the network. Then I will switch gears a bit to talk a bit about centrality. Centrality algorithms help us determine the influence or popularity of nodes within a network. One of the simplest measures of evaluating popularity in a network is by calculating the degree centrality for different nodes. In the context of social media, we can think of individuals as nodes and whether someone is following them as the edge. That's the relationship that we're effectively counting in this network. And to calculate degree centrality, we simply count the number of followers a person has to evaluate that popularity. So intuitively, an individual with 10 million followers on Instagram is going to be more popular than an individual that has just 10. And in sticking with our example on the screen here, we can count the number of edges or relationships our central node has as 8. So this would mean that this particular individual in this social network has 8 total followers. Additionally, we can evaluate the influence or criticality of a node in the context of the flow of information throughout the network by calculating the betweenness centrality. Betweenness centrality is calculated by finding the shortest path between all nodes within a graph. The betweenness score is the number of shortest paths that pass through the node. So in the above example, we can see that the highlighted green node sits in between two relatively connected clusters of nodes, and the only way to traverse between the two clusters is through the node with the highest betweenness. This node, therefore, is critical to be able to be traversing throughout the graph. So with that, let's just take a look at a very brief example. If I wanted to traverse from node A to B through the shortest path, I do need to go through our critical node in the center in order to be able to do so. And similarly for nodes C and D, the shortest path also runs through this critical node. So as we calculate more and more shortest paths, we eventually find that most of them run through our center node here, thus making it a really large influencer for this flow of information and thus having a really high betweenness score. I guess like path algorithms, there are some common implementations of centrality algorithms that you're probably familiar with as well. And thinking back to the social media example as before, this highlighted node would effectively be a person that serves as a connection between two different communities. So let's say that this highlighted node is my profile on LinkedIn. If I wanted something a colleague of mine posted to reach another grouping of nodes that they were not directly connected with on LinkedIn, I could serve as the bridge between the two groups to help get messaging across to individuals that may not otherwise have seen it. Another example of this would be to think of a shipping hub, like a distribution or fulfillment center that stages products before they're shipped out to retail stores. This distribution center would constantly be receiving all sorts of products before they're loaded onto trucks that are eventually shipped to their final destination and can be put into the hands of my customers. It'd be important, for example, to understand where these choke points are in a given network and ensure that there was enough staffing or support within this particular distribution center so that I would be able to fulfill, the demand farther downstream at my retail stores. And finally, another example would be to think of something like an electrical grid. There are power stations in the country that are critical to electrical infrastructure, and there are inherently some that, end up connecting large swaths of towns or regions. And if they were to go down, it would result in the transmission of electricity really being interrupted between two regions. So that's a bit on centrality algorithms. We'll now dive into our last bucket, community algorithms. So as the name suggests, community algorithms help determine how connected and intertwined nodes are within a graph and their underlying communities. They're a bit different from traditional classification or clustering algorithm, as those don't necessarily consider the many relationships that may exist between nodes within a graph. A tangible example of a community detection algorithm would be to use something like Louvain modularity to calculate communities of products that follow similar purchasing patterns. So let's say, for example, we're analyzing products sold at a grocery store. If we consider our graph's nodes as products and the edges the number of times products are purchased together, we can perhaps understand and hypothesize an underlying trend that may not have been one that we would have been able to uncover intuitively. So two of the more interesting pairings you may be able to pick up on are frozen vegetables being purchased with ice cream and marshmallows being purchased with charcoal. So in the first instance, with ice cream and vegetables, we have two seemingly opposite items on the health spectrum, but our data is indicating that they're being purchased together quite often. And while it may not seem like these items, really should be purchased together with one another very often, further analysis of our freezer display shows that these two items are actually stocked next to one another within our stores. Knowing this information could help us with the analysis and placement of these types of items within our freezer planogram within the future. In the second instance, we have marshmallows and charcoal being brought together and identified as being within the same community. Again, perhaps not very intuitive, but our algorithm could be detecting the seasonal purchasing behavior of these two items peaking in the summer due to our customers making s'mores outside when the temperature becomes warmer. So these are just two examples of communities being detected within a given point of sale dataset. But when our scale is in the context of tens of thousands of items across hundreds of stores, we can bubble up these really hidden insights and really use them to our advantage in better understanding our customers and really deriving meaning from previously hidden communities. So that was an introduction to different kinds of graph algorithms. Now, I'll briefly touch on some of the different technologies that you can use to store your graphs and run these algorithms on top of them. So first, we have our graph native databases in Neo4j, TigerGraph, and Onzo. Our demo today, as Jake has mentioned, will be done in Neo4j. And these are enterprise-grade tools that are built specifically for storing graphs with millions upon millions of nodes and edges. So running multi-hop queries using these technologies and applying these graph algorithms we talked about can be done with ease. Additionally, these graph native tools have partnerships with AWS, GCP, and Azure as well. For those that are familiar with Spark, there are actually ways that we can represent nodes and edges within a tabular structure called a data frame. We store these nodes, edges, and properties as we would store other kinds of data within a table, and as a result, we're able to run graph algorithms on top of it. And finally, in addition to the graph native databases being partnered with the large cloud vendors themselves also have their own graph database offerings as part of their suite of products. And with that, I will turn it back to Jake to conclude our day with another demo.
Thanks, Brendan. We're going to be using the same manufacturing data set from before, but now we're going to be trying to answer this question of doing a survey of our key sites in our network. In this case, we're looking at the key linking points or potential bottlenecks. And these are places where we could look to potentially add redundancy in our supply chain. So for that, let's hop back into Neo4j and take a look. I'm going to go ahead and clear out what we have from before, and I'll build back our manufacturing network. So when we're looking at the bottlenecks in your process, the question that we're trying to answer really is where is the most flow coming through? And in order to do that, we want to be able to use a weight here. So we're going to be using our delivers attribute and the number of units that get delivered from each site as this weight. And this will help us determine the strength of the relationship and the flow of our data in our network. We can use this quantity amount as an input for our centrality algorithm. So in this case, because we're trying to look at the flow and where the most flow is coming through each site, we're going to be using betweenness centrality. In Neo4j, they have this graph data science plugin that makes it really easy to run the algorithms that we've been discussing. So I can go ahead and add my algorithm. I'll choose betweenness. And I'll go into settings and I'll make sure that we have our quantity amount used as the weight. This algorithm will take into consideration the direction of flow in our graph, as well as the number of units that are being delivered. I've gone ahead and ran the algorithm, and I've applied a color gradient as well. So if we take a quick zoom out, go ahead and make this smaller. The darker the node means the higher the centrality score, which means it's a more important node in terms of the flow of goods across our network. I can go ahead as well, and on the node itself, I can add this score as well. Because as Brendan mentioned, it's just a mathematical calculation checking for the shortest path between all nodes. So what this tells us is that these darker nodes, such as site 2 and site 4, are along the shortest path between other nodes. So we think of site 5, for example. How would site 5 get to site 12? Well, it would have to go through site 9, site 2, and finally to site 12. And in our example, it's pretty easy to figure out, okay, these nodes are in the middle, they're probably like in the intermediate, and if we had to make a guess, our traffic has to flow through these nodes if they want to make it to these final nodes. However, in a large manufacturing data set of hundreds of sites, thousands of sites, the score of each individual site will be much less obvious. And we could easily run this exact same process, even though the scale is much larger. And from there, we could take these scores and save it to our database, save it into our graph, and use it as an attribute in other reporting. Potentially, we could use it as a feature input for a downstream machine learning project and go from there. So if we take a step back, in this example, we were specifically looking at the key sites in terms of material flow in our data, so we use betweenness. But we can think of a related question as a result of this analysis. So if we're thinking about what sites are going to be closed, or if we know, for example, that this site will be closed in the future, we want to know the impacts both up and downstream, and especially if it has a high betweenness score, we want to be accounting for the scenario. So I've already written a custom query using Cypher that will allow us to do this sort of analysis. So we'll take a look at the delivery paths going to and from any site, and we'll let us trace the flow. So I can go ahead and upstream sites, and I'm taking a look at site 4 in this example, and I've also parameterized this amount of how many hops we want to look at. So in this example, our network's pretty small, so it doesn't really matter. But if we're trying to think of what are all the downstream impacts, I could type, 100 hops away, and I can see my entire network. Or if I'm just looking at the first or second or third immediate impacts, we can go ahead and do that as well. So I've gone ahead and ran the query, and we can see that we found these 4 nodes. All of the nodes that have been found will be highlighted, and this makes sense. We're looking at site 4, we can see all of the upstream analysis. This will only become more important in a large data set, as it's easy to understand here just graphically, but if it's not as intuitive, it will be a lot harder to trace this. We can easily change this query to make it more complicated as well. We can write a query to only search along paths that deliver a certain component, which will allow us to trace the flow for that one specific component really easily. We could easily change it to answer this and any other related analysis. We could do a similar exercise for our components as well, where we want to see what are the input components for any other item. Or alternatively, if we have a completely separate question, we could write more advanced queries altogether. So far in this demonstration, we've only looked at the quantity delivered attribute on this relationship. But depending on your specific use case or whatever question you're trying to answer, we can imagine some other potential useful attributes here. Some of the examples may include the frequency of shipments between 2 different sites, or potentially the average cost of shipments by different travel methods, which is similar to the shortest path example Brendan mentioned earlier. We can store any and all of these as measures on our relationship and use some of the algorithms and Cypher queries that we've talked about in order to gain further insight. So there's quite a level of flexibility in Neo4j and some other graph technologies. We can see in Bloom that there is a data science plugin that makes it relatively easy to run these algorithms out of the box. So we've been talking about betweenness. We also mentioned degree centrality and Louvain community detection as well in our presentation. But it's really quite simple to go ahead and once we have our data up and running, to go ahead and do some exploratory analysis here. Other graph technologies like TigerGraph do provide similar functionality, so it's not just tied to Neo4j. We could also connect to these graph databases from wherever we most commonly work. So one example may be using a technology like Azure or Databricks notebooks and running analysis there using Python drivers. So we connect to our Neo4j graph database, but run the analysis in an interface that's more familiar to you or your group. So overall, graph technologies can fit into your data stack and are quite flexible in terms of whatever your specific business need may be. Hope this has been a useful primer into working with your graph data. I'm going to jump back to the slides for some final considerations and takeaways. Overall, We've established that graphs and relational database systems have unique roles for modern data organization, and they can coexist. Graphs, pivotably, store properties on nodes and their related edges. This allows us to run complex and unique analysis based on this graph structure, which includes shortest path, centrality, and community detection. With all this in mind, we hope that you have a better understanding of the value and applications that a graph database can take on. And if you'd like to learn more about how you can best apply graph at your organization, please don't hesitate to reach out. With that, we've come to the end of today's session. Hope you found this useful. Thank you for joining. Have a nice rest of your day.